Okay, this is video 30.3. We're going to learn about Ampere's Law. And Ampere's Law is a tremendously useful thing that we can use to calculate magnetic fields, and it's much, much easier than the Biot-Savart law. But in order to understand it, we need to know about something called the line integral. Because Ampere's law is like Gauss's law, but for magnetic fields. But instead of a closed surface like Gauss's law uses, we used a closed loop. So the idea is that we'll have some loop. It's going to be closed, but other than that, no constraints on its shape. In practice, it will usually be circular. And we'll have to go around this loop in a particular direction. And what we'll do is we'll break it up into a lot of small ds's. This is not a wire. This is an imaginary loop called an Amperian loop. But ds is a vector, and it points in the direction that you're going around the loop. Now at every point along the loop, there's going to be some magnetic field. And that magnetic field might happen to point in that direction here, this direction here, so you might have a magnetic field in different places. Now for every one of those ds's, you're going to calculate the dot product B dot ds. Remember the dot product, we have to know the angle between B and S, that B dot ds is equal to B ds times the cosine of that angle. If the magnetic field happens to point in the same direction as the loop, and we want it to, then B dot ds just becomes the scalar B ds because cosine 0 is equal to 1. And the idea is you'll add up all of those B ds's. What I want you to understand about the line integral is that we are almost never going to evaluate it as an actual integral, but you need to understand what's going on when we use Ampere's law. Now getting to what Ampere's law actually says. The line integral, B dot ds, and it's written with a little circle on the integral, which indicates that it's a closed loop, equals mu naught times the enclosed current. So the idea is that you've got your Amperian loop, and you've got wires carrying currents into or out of the loop. And you might also have other currents out here. But just like Gauss's law, where any charge that was outside the surface didn't matter, any currents outside the loop don't matter to the value of this integral. So for calculating B ds for this loop, we would say that B dot ds will be extremely hard to calculate, but whatever it is, it will equal mu naught times I1 minus I2 plus I3. Now the reason I subtracted I2 is that it goes into the page, whereas the other two are coming out of the page. It's not particularly important which direction you take to be positive, but you do need to say that if you have two currents pointing the opposite direction, you subtract them to get the net current. Just like Gauss's law, Ampere's law is only useful when you have a lot of symmetry, usually circular symmetry, and that's what we're going to be looking at next. Is our old friend, the field of an infinite straight wire. When we used the Biot-Savart law for this, we got a result, and that result was nice and compact and beautiful. Unfortunately, getting there required about 2 pages of calculus. Ampere's law will make that much easier. So here's our wire, carries a current I. What we'll do is we'll draw a circular Amperian loop around the wire. So here's our Amperian loop. Now we also know to expect that the magnetic field will circulate The magnetic field goes in circles like this. So if we look at this particular ds, B at that location points in the same direction as ds. We also expect B to be the same value at every point in the loop. So Ampere's law says B dot ds equals mu naught times the enclosed current. Enclosed current's easy, that's just I. But B dot ds, because B points in the same direction as ds, that's just B ds, we can dispense with the vectors. And also, since we expect B to be the same at every point on the loop, we can bring it out the front of the integral. So we have B times the integral of ds equals mu naught I, just mu naught I. And the integral of ds is the arc length of the loop, which is 2 pi times r, where r is the radius of the loop. And that becomes B equals mu naught I over 2 pi r, which is the same result we got from Biot-Savart law, but in 3 lines of algebra and no heavy calculus. So this is why we like Ampere's law. And Ampere's law will also enable us to calculate the field inside a wire, which is possible with the Biot-Savart law, but it is an enormous pain. And I know that because I've done it in graduate school and hope you never have to. So inside the wire, we're no longer assuming that the wire has 0 width. In fact, the wire will have radius capital R. We're going to assume that the current is distributed throughout the wire. And we can define something called current density, which is the current per cross-sectional area. So it's the total current divided by the cross-sectional area of the wire, and if it's a circular wire, that cross-sectional area is pi r squared. What we'll do is we'll draw an Amperian loop inside the wire, and I'm going to draw an end-on view of the wire. So here's the wire, it's capital R, and we have current distributed across it. We'll draw our Amperian loop like that. And once again, because of symmetry, we expect B to point in the same direction as ds all the way around it. So when Ampere's law says the integral of B dot ds equals mu naught I enclosed, B dot ds is once again 2 pi r times B, where little r is the radius of the Amperian loop as opposed to big R, which is the radius of the wire. And we're left with figuring out what the enclosed current is. And it turns out to be equal just to the current density times the area of the Amperian loop. So J times pi little r squared. And that, if we do a bit of algebra, works out to be I over pi big R squared times pi little r squared. This is J here. So pi's cancel. And we're left with B, after quite a bit of algebra, mu naught over 2 pi times little r over big R squared is the field inside a wire. Notice that it's 0 at the center, which doesn't surprise us, and it increases linearly until we get to the outside of the wire, just like the electric field inside a sphere of uniform charge density, which is kind of interesting. Probably not an equation you should memorize, but definitely something you should be able to derive, because Ampere's law will be on the test. Biot-Savart law may not, but Ampere's law is guaranteed to be, both on the classroom test and AP. Tomorrow I'm going to check questions 6 through 8, all of which deal with Ampere's law and in particular the meaning of the line integral.